All right, any questions? No? Tell me a way you can make calcium oxide. If somebody asks you to make some calcium oxide, what's one way you can make calcium oxide? I'm sorry?
Are you asking how to make calcium oxide?
Yeah, how can you make some calcium oxide? What's one way?
Heat the calcium carbonate.
Okay, you can heat up calcium carbonate. That's a good one. Heat up calcium carbonate, you get CO2 and calcium oxide. You know, what kind of reaction would that be? Well, that turns out to be a... That's not a redox. For example, if you take calcium carbonate, solid, heat it up to get calcium oxide and CO2 gas, the oxidation states don't change. You should be familiar with two ways of doing oxidation states. Your standard Chem 1A, Chapter 3 way, right? What are the oxidation states here? Which goes first? +2 for calcium? Well, then oxygen at -2, and then carbon at +4. Which goes first? +2, -2. Which goes first? -2, +4. The oxidation states change. No, the oxidation states didn't change, which tells you this is not a redox reaction. Is this a metathesis reaction? Is it a metathesis reaction? No. How can you tell it's not a metathesis reaction? Because metathesis reactions are ion combinations. This is not metathesis. This is a acid-base reaction. This is acid. If there were an infinite number of categories, then we wouldn't know. But you know, there's only one category left, and we eliminated two. This is a process of elimination. This has got to be acid-base. Is this a Bronsted acid-base reaction? No, this is not a Bronsted. So let's do process of elimination. That leaves Lewis. This is a Lewis acid-base reaction. And so we'd want to draw out the Lewis structures and see mechanistically how this happens. You know, how does Lewis acid-base reactions happen? You rearrange the electrons. After you do a bunch of these, then you'll know CO2 is classified as a acid. It's a, not a Bronsted acid, it's because it's not a proton, it's a Lewis acid. Okay? Lewis acid. CO, if CO2 is a Lewis acid, then CO must be a Lewis acid, right? CO must be a Lewis acid, right? If CO2 is a Lewis acid. Is that good?
Reason?
Yeah. No, it isn't. CO turns out to be a powerful... What would you think? What looks unusual there? Well, two things. One is the oxygen. Right, but even if the oxygen gains another pair of electrons, is that really going to change? Let's see, can the oxygen be attacked? Gain another pair of electrons? What would it do? It'd push out? And would it change the formal charge? No, actually, it doesn't. If you bring in a pair, here, boom, so we still have 3 bonds in a lone pair. It doesn't change the formal charge. And so what stands out about this is not the oxygen, it's the carbon. The carbon, normally carbon, do you think of carbon as being all that reactive? No, but in this case, carbon's very reactive. Why is carbon so reactive? How often do you see carbon with a negative formal charge? I see it in carbon monoxide, in cyanide. Cyanide has the same, you can do cyanide in either valence bond or MO. This is, what's the oxidation state? Oh, not oxidation. What's the formal charge on carbon in cyanide? Formal charge.
Minus.
Cyanide has a net, the formal charge on nitrogen is 0. Cyanide has a net negative charge. It's an ion. Right? Cyanide ion, Cn minus. So, do you see that? Both cyanide and carbon monoxide have a negative formal charge on carbon, which makes it unusually reactive in terms of what?
Lewis acid.
Yeah, in terms of Lewis acid base, making it a powerful what? Lewis base. So carbon monoxide and cyanide are powerful Lewis bases. They want to find Lewis acids to react with. And so they're going to react similarly in Lewis acid base reactions because of that. And so what we do is, still we have to analyze the structure. CO2, however, is a Lewis acid. It's not that powerful, but those are two powerful Lewis bases right there. This is one way of making it, but it's an acid base. Give me a redox way of making calcium oxide. Well, the easiest is just to take calcium, which has 2 valence electrons, and oxygen, O2, and we'll take 2 of these calciums and 1 O2 and react that to form, well, what happens? What happens is there's going to be some rearrangements and some collisions, but essentially what's going to happen is this bond's going to break, leaving an electron here, here, and here, right? And then we have 2 of these, so actually rather than writing 2 here, I'm just going to go ahead and draw out 2. And then we end up with this. In other words, calcium loses its valence electrons, oxygen gains those and gets the octet. And so we end up with calcium with no valence electrons and oxygen with all an octet. Does that make sense? This is called an element plus element combination reaction or redox. That's one I forgot to write on there. And so A, element plus element. You guys have done this to figure out what the formula is going to be, right? The formula. The formula for calcium oxide is going to be CaO. The formula for sodium oxide would be Na2O. You've done these. So element plus element is Chem 4, so that's why I didn't think of it when I wrote this. Actually, I have a modified version of these PowerPoint. This is an older version, and I fixed those things. This is 2011, but one of my computer hard drives crashed, and I lost a lot of files. I didn't have them backed up. But there should have been element plus element, so I know there's a version of this floating around which is corrected. Then we have other redox reactions. Single replacement, this is discussed in Chem 4 and Chem 1A. Combustion, Chem 4 and Chem 1A. The chart method is not discussed. The chart method is my name for it, but this is a simple method. Potential diagrams, which is a more complicated version of the chart method, and skeleton redox. And so we'll be talking about these in our review of redox. Some of this is review, some of this will be new. Basically, I'm going to skip single replacement. Do you know why I'm going to skip single replacement? Because how many of you have memorized the exceptions for single replacement reactions? It works for all these, but it doesn't work for this. How many of you have those memorized? The exceptions. Does single replacement always work? No, it fails for certain types, right? So for example, if you use a mineral acid, single replacement works. However, if you use an oxidizing acid, single replacement fails. Do you have that memorized? No? How many of you have more than one pattern memorized for single replacement? A plus BX versus the X2 plus AX pattern. Or no, AY. X2 plus AY pattern. Do you guys have the X2 plus AY pattern memorized? If you do, then great. You know, continue using single replacement because then you'll know where it fails, right? Well, single replacement is great because it's quick and easy, but since you have to memorize those exceptions, then it's fine if you have it memorized, but if you don't have it memorized, then you have the potential for getting the wrong answer. And so a more general method would be something, the chart method here, when you don't have to memorize the single replacement. The chart method will cover it, you know. And so I'm not even going to talk about single replacement. I'm going to just go straight to the chart method. The redox chart method is so easy. You know, we inventory the species just like acid-base. We find the strongest oxidizer present. Here's the chart here. This is from chapter 20. You look fluorine, lithium. These guys you place in here based on the numbers over here. You know, because it looks like the worst reducer is not lithium. It looks like the worst reducer is hydrogen and hydroxide. But that's not the case because that's minus 0.828, which brings it right here. And so that's important. This last one's very important here. This is water as an oxidizer. I know it's hard to read, but anyway, this is the chart. So we find the strongest oxidizer present. We find the strongest reducer present here. And then number 4 is we combine the strongest oxidizer with the strongest reducer. Oxidizer I call OA for oxidizing agent. Reducer we call an RA for reducing agent. We combine those two by combining the half reactions. When we combine the half reactions, we have to make sure that the number of electrons consumed is equal to the number of electrons produced. That is, we can't have leftover. We can't have an excess of electrons, and we cannot have a deficit of electrons. The electrons have to be properly balanced. Otherwise, it doesn't work. And that is, you know, electrons, I mean, could you make a 1 molar aqueous solution of electrons? It's not going to happen. Not in water. You know where you might be able to make a solution of electrons? This is unusual. You know, do you think lithium is the most powerful reducing agent in the universe? Do you think? No. Definitely not. This is more common. There's much more powerful reducing agents. There's one extremely powerful reducing agent that I used to use in the lab, and it's just a solution of electrons. Well, how do you get a solution of electrons? Free electrons. One way of generating a solution of electrons is to liquefy ammonia, and so you have a pool of liquid ammonia, and then you dissolve sodium metal, and so you'll have sodium ions dissolved in that, and you'll have electrons, and the electrons separate from the sodium ions, so you could have these mobile electrons in this, and the whole thing glows with this intense blue color. It's very very pretty to look at, but it's very reactive because it turns out to be extremely powerful reducer. And so you could reduce things that are very reluctant to be reduced, you know. Well, anyway, we go through that. Simplify. For us, we're never going to have a solution of electrons, right? We're dealing with aqueous solutions. It's not going to happen. We simplify if necessary and determine if a driving force is present. The driving force is going to be going from stronger oxidizer to weaker oxidizer, stronger reducer to weaker reducer. Since there's a conjugate relationship, if one of these is true, the other must be true. And so typically we just look at one, the other must be the same. But this is a good way to double check, because if one is true, the other is false, then you did something wrong. Okay, this method yields the NIE, and normally we just stop there. We don't try to get the CE and the IE, we just leave it as the NIE. Nitric acid is called an oxidizing acid. Why? Because all acids are oxidizers. Why are all acids oxidizers? Because they have H+. So H+ is a decent oxidizer, a moderate oxidizer. But oxidizing acids are unusual because oxidizing acids have something more powerful than H+ as the oxidizer. And so what you want to do is you want to familiarize yourself with the one thing that a lot of students never do is really look at a table. A lot of students, all they do is that there's the table there, they know it's there, why bother looking at it? Why bother looking at it, because I always have it. I can just look up what I need to look up, right? But then you're at what you call level 1 as far as, science goes. You're just nothing special. Anybody could do the same thing you're doing, just looking up a value on the table. You don't need any kind of skill or knowledge to do that, right? And so that can be outsourced wherever, because anybody can do that, look up a value on a table, right? And so what you want to do is, when you look at tables, you want to try to see what? Patterns. Try to see patterns, or at least get familiar with tables. Right? Because if you see a pattern, then if something's not on the table and you know the pattern, then you can kind of figure out where it belongs, right? And that makes you much more powerful, because a person who only knows the table is going to say, hey, it's not on the table. Can't do anything, right? It's not there. You never said anything about this. We're not responsible for this. It's not there. You might have said this too in the past. Where did this question come from? The teacher never talked about this. The teacher never said anything. We never saw this in the book. This is not fair, right? Then I know, okay, this person's at level 1, They really aren't at the next level would be, to actually kind of figure out based on what they've seen before, right? And kind of come up with some answer. And so one thing I don't like is blank. If I see blank and no attempt at solving, just attempt something, I give partial credit. And so just try to come up with some idea based on some kind of pattern that you might have seen or done. But, I try not to throw too many questions out like that, because I do get a lot of complaints, I get a lot of complaints. I've never seen this on the test, or you never told us about this. And so I want to say, you get a lot of those types of questions because, not everything's going to fit on this. So anyway, what you want to do is you want to kind of familiarize yourself. Do you see any kind of pattern? Well, it doesn't look like there's much of a pattern there, right? But it turns out there are multiple patterns in here that you sort through. Multiple patterns, things like fluorine versus chlorine versus bromine versus iodine. That's an easy pattern. Which one should be the most powerful oxidizer? Fluorine, chlorine, bromine, or iodine?
Fluorine.
Fluorine, why?
It's the most electronegative.
It's the most electronegative, 1, and 2, its size. It's the smallest, right? It's going to have the highest Z effective. You guys remember Z effective? It's going to have the highest Z effective, which is going to make it the one that's going to attract electrons the most. But not only does it have to attract electrons, it also has to hold on to them. Right? And we had things like electron affinity, but I'm not really going to talk about electron affinity. Electron affinity, which one has the highest electron affinity? Chlorine. And so shouldn't chlorine be the most powerful oxidizer? If it has the highest electron affinity? Why isn't it the most powerful oxidizer when it has the highest electron affinity? That doesn't make sense, does it? And so what should we believe? Should we believe electron affinity? Or should we believe experimental fact? We believe experimental fact. Experimental fact tells me that fluorine is going to be the most powerful oxidizer. And whatever we use for theory, or whatever else, has to agree with experimental fact. If it doesn't, then there's something wrong with it. And so electron affinity doesn't agree, but there must be something wrong in the way we're using electron affinity or the way we are understanding electron affinity, because experimental fact says something else. Now, electron affinity is so narrowly defined. Do you know what electron affinity is? It's for the gas phase. You're taking gas phase to gas phase. Now it makes sense. Now it clicks, because I know gas phase isn't taking into account full reactions. When we're looking at reactivity, we always look at the reactivity of the reactant, but we also look at the stability of the product. Now, if you have a gas phase ion, is that very stable? No. And so what kind of products does it form? And so the products that typically form, well, in this case, the product is going to be fluoride AQ versus chloride AQ. We know fluoride AQ is going to be more stable. Why? Than chloride AQ. Versus gas phase. If this were electron affinity, this should be gas, 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 right? That's electron affinity. And so electron affinity is not wrong. Electron affinity, I just didn't look at it carefully enough. And so it doesn't really apply here. And so when we're looking at the aqueous phase, fluoride AQ is more stable than chloride AQ because what? Yes, smaller size. Do you guys know what I mean by size? When we're talking about size, this is back in chapter 13. When we're looking at electrical attractions, it depends. If I have a fluoride in a water, versus a chloride in a water, which one of these will have the stronger attraction? The fluoride in the water. Why? Because it's smaller. It's smaller, therefore the distance is closer. And the closer they are, the more they can interact. Well, you're thinking, is it really the distance closer? Well, it's the distance to the center of charge here. So even if these are touching, we're looking at the distance to the center. Well, the distance to the center, rather than saying distance to the center of charge, I like to say charge density. Charge density is the charge to size ratio. And so if I have my negative charge spread out over a bigger volume versus the negative charge concentrated on a small volume, obviously this is going to have a stronger attraction. And so this is why I like charge density rather than looking at magnitude of charge and distance between center of charges, as in Coulomb's law. Anyway, and so the fluorides are going to be stabilized by having waters, because we know that charge separation creates unstable. You can have voltages. There. John Carl. Oh, it's okay. I see. I thought. Okay. What else? So here, the same thing happened for what? For lithium. Remember lithium? From yesterday. Well, anyway, we get familiar with these types of things, and then we try to reconcile things that just don't make complete sense. And so we can compare those. Ozone, yeah. This is interesting. What's the oxidation state in sulfur in this? +7. The oxidation, how many valence electrons does sulfur have? 6. If it's plus 7, that means it must have lost 1 core electron. Can you see why this is such a powerful oxidizer? Number 3 on the list, because it's lost a core electron. Losing a core electron, that's not stable, right? And so here, hydrogen peroxide, oxygen's in the -1. It wants to be -2, right? Hydrogen peroxide's weird though, because hydrogen peroxide is what we call the amphoteric equivalent of redox. Hydrogen peroxide can go either way. Hydrogen peroxide can be an oxidizer or it could be a reducer. And so we don't call it amphoteric because amphoterics are reserved for acid base, right? Either way it can go. And so it would be the equivalent there, here. Whereas this would only be an oxidizer, this would only be an oxidizer, this would only be an oxidizer. And so this is the first one that can go either. Oxygen can either gain an electron to go to -2 or can lose an electron to go to 0 and form oxygen gas. Permanganate, can that go either way? Can permanganate go either way? Well, what's the oxidation state on manganese? +7. So here's manganese. +1, +2, +3, +4, +5, +6. +7 means it's isoelectronic with argon. Can it go +8? No, because we lose a core. And so permanganate doesn't go both ways. Permanganate is only a oxidizer. And so a lot of these species can react either way. And so you'll see hydrogen peroxide on both sides of the chart. You'll see some of the other species on both sides, like water. Water can go either way. It can be an oxidizer or reducer. And so what you do is, you read through the chart every once in a while to just familiarize yourself, because the first step in pattern recognition is just to kind of get a feel. You don't sit there and memorize it and then just reproduce it. You just look at it and you kind of look for patterns and kind of see if you can see how things react. One of the things you'll start to notice when you start looking at the patterns is this. Like nitrate and H+. Nitrate and H+ makes what? If you have nitrate and H+, that's called nitric acid. And so this is nitric acid. And the interesting thing about nitrate is it's a fairly powerful oxidizer. When you have a normal acid, like acetic acid or something like that, that falls here. In most acids, the anion is like a spectator or is unreactive, And so here, in most acids, which are all labeled mineral acids, the anion doesn't really participate in the redox reaction. But in this case, nitric is a special acid, and we see another special acid here. Do you see another special acid? I see one here. This is another acid. What's this acid called? What's this anion called? Iodate. And so this would be called iodic acid. Iodic acid is also an oxidizing acid. Why? Because iodate is a pretty good oxidizer. Why? For chlorate's not here. Perchloric acid is another one, the strong ones. This is called manganic acid here. Dichromic acid. Name it the acid. It doesn't have to be the acid though. In redox, you don't have to have the acid. So, for example, I don't want to go buy this this permanganic acid, right? Instead, I can make this solution. How can I make this solution? I just take some potassium permanganate and mix it with some strong acid, like HCl. And then I can make this solution. And so they don't have to come from the same source. There can be multiple sources for this. We do need the H plus though. Why do we need the H plus? So for example, is iodate as powerful of an oxidizer without the H plus? What is the purpose of the H plus? Do you see a pattern? H plus, H plus. A lot of these require acidic solution, H plus, strong acid. Or it could be weak acid too, it wouldn't be as reactive maybe. But it requires acid. Do you see a pattern there? With the H plus? In an effort for time, to save time, I'm not going to spend much time talking about it. But yes, there is a pattern with the H plus. What is the pattern? You form water. Water is often a product. Where does that H plus end? It ends up here. We go from hydrogen plus 1 to hydrogen plus 1, the oxidation state, so nothing really changes, but we do form water, which is stable. If we didn't have H plus present, what would we form? We'd form, not H2O, we'd form oxide. Is oxide stable? No, oxide's a powerful base, right? It's not stable. Water is stable. And so H plus, there's a pattern there, and there are other patterns we'll try to look for. And so one of the things I know, nitric is such a common acid. I know that nitric is kind of a dangerous acid compared to like HCl. But even though HCl is a stronger acid, I always worry more about nitric acid. Why? Because usually when I'm dealing with HCl, I don't have to worry about redox too much because it's just a moderate oxidizer, right? But when I'm dealing with nitric, I always have to worry about redox because nitric is a powerful oxidizer. And so not only am I worrying about my acid-base reaction, I'm also worrying about my redox reaction because there's potential for, especially with strong oxidizers, a potential for explosions, right? Violent reactions. And so, if an oxidizing acid didn't appear on the chart, could you tell it might be an oxidizing acid? How could you tell? Like HCl. HCl is just your normal typical acid, H plus and Cl minus. Is Cl minus a powerful oxidizer? No, Cl minus would be not a powerful oxidizer. Cl minus would be a reducer. Is it a very good reducer? No, remember the conjugate relationship. Chlorine's a powerful oxidizer, therefore chloride must be a weak reducer. So as far as redox goes, I don't worry about chloride. Unless you mix it with potassium permanganate. Did you guys do this in Chem 1A? HCl and potassium permanganate? HCl and potassium permanganate. The permanganate's going to not attack H plus because are there any electrons left on H plus? No, permanganate's going to attack chloride to form a green, yellow, corrosive gas called chlorine, and you should have done it in the hood because you're generating chlorine gas. I think some people didn't do it in the hood, and you could smell the chlorine gas, right, in the lab. Do you guys remember this one? And experiment 18. I don't know. Maybe we ran out of time. Well, anyway, so nitric, nitric's special, and you'll start to see other acids that are special. But for copper and nitric, how would you handle this? First, you inventory. So copper, what is it? Is copper Cu2 plus or Cu solid? Cu solid. Nitric acid. Nitric acid is a strong acid, so it's H plus and nitrate. Do we have anything else in here? Water. H2O liquid. Since this is a review, bear with me since I do this in Chem 1A. also, but I'll just use the same example. Well, this is the chart method. But, a lot of people say, the chart method is too much work. Why not just do the single replacement method? I could do it a lot quicker using single replacement. Do we form copper 2 plus or copper 1 plus? Copper 2 plus or copper 1 plus? Why? Why not copper 1 plus? Is it possible to form copper 1 plus or impossible? What are the two common charges of copper? 1 and 2. So which one are we going to form? 1 or 2? 1 or 2? I don't know. It could, but you know what? If you looked at the redox chart, at least this one, if you looked at this redox chart, you see copper metal only appears once on this side, here. And what did it form? Copper 2. So if you looked at this redox chart, then you'd probably suspect that copper 2 is more favorable than copper 1 because they didn't even bother putting copper 1 on this chart. You see? And so here's where we're just using some kind of pattern to kind of figure out which one we should form. And so the person who writes copper 2 will be definitely at an advantage over the person who wrote copper 1 nitrate. Oftentimes I get people writing copper 1 nitrate here. This is a coin toss, but it isn't the coin toss, right? There's some factual knowledge here in addition to it. You'll see copper 1 in the appendix though, appendix D. So what's copper 2 nitrate? Its formula. Yeah, Cu with 2 NO3s. Solid, liquid, gas, or AQ? AQ. Nitrates are all soluble. And hydrogen. Single replacement assumes what? This is the A plus BX pattern. Tell me the assumption for this pattern. This pattern assumes what? This pattern assumes that A is always the reducer, B is always the oxidizer, and X is always a spectator. Is that always true? No. And so here's where it fails, because X is not a spectator. X is even more powerful than B. Although you need the H+. The H+ doesn't actually do the oxidizing. The H+ is just to form water at the end. And so this failed. This is wrong here. This is wrong. It fails. But if you have it memorized, this is an oxidizing acid, you shouldn't be using this for oxidizing acids, right? Or even better, X is not a spectator. X is the most reactive species here. Right? That's even better. And so here, as we go through this, we just go through the chart. Copper only clears on the reducing agent side. Hydrogen plus only clears on the oxidizing agent. Nitrate appears as the oxidizing, but it's got to be nitrate with H plus here. This is just H plus alone. And we need that H plus because if we don't have that H plus, then that weakens nitrate's ability. In Chem 1A, I just told you if the H plus isn't there, just omit it. In Chem 1B, we're actually going to do calculation, and see how the H plus concentration changes its position in the chart. That's Chem 1B style calculation. Water is both an OA and an RA. And so we just use the chart. We go through the chart and pick the strongest OA. We have 3 of them. Which one's the strongest oxidizer? The strongest oxidizer is the combo of H plus and nitrate. This is the OA. And then we look, what's the strongest RA, reducer? Copper. Okay, then we copy down the half reactions. We just copy them off the chart. We don't do anything else. And so copying it down, nitrate plus 4H plus 3 electrons yields NO plus 2 H2Os, liquids. NO is a gas. So we just copy that down. And then copper, we copy it down, but we reverse it because we're starting with copper metal. On the chart, it goes from copper ion to copper metal, so we flip it, and we go from copper metal to copper ion. You know, both of these, you could do in either direction, but we need our reactants at the same time. And so I flip this equation. This is flipped. And then I combine these 2 equations, making sure that the electrons consumed, 3, equals the electrons produced, 2. Well, they don't equal right now. And so what I have to do is I have to make them equal by changing the stoichiometry. That is, the coefficients here. And so rather than saying 3 electrons consumed, I should bump that up to 6. And so I'm just going to multiply this one by 2. And then rather than saying 2 electrons produced, I'll multiply this one by 3. And now the electrons produced equal the electrons consumed, and I can just add it up. And so I'm going to have 2 nitrates plus 4H plus 6 electrons. The 6 electrons should cancel, so I'm not even going to write that. Oops, 8. 8H plus 3 coppers, solids, yields 2NO, gas, plus 4H2O, liquid, plus 3Cu2 plus, AQ.
Isn't it 6 electrons instead of 3 copper solids? No, it's 100%.
It's going to be 3. 3 times 2 gives us 6.
Oh, it's already combined.
Yeah. I already eliminated electrons. Next, we have to look for the driving force. When we look for the driving force, we have to figure it out. Oxidizers take electrons, and so this is the OA. It's consuming the electrons. We do this, the easiest way to figure out the driving force is to use the half reactions. Because if this is the oxidizer, then this must be the conjugate reducer. And so this must be the reducing agent on the product side. In other words, if we were to reverse this reaction here and go backwards, then this would be losing electrons, not consuming electrons, or producing electrons, right? Over here, going forwards, this would be the reducer because it's producing or giving up electrons. And this would be the oxidizer because if we reverse this, it would be consuming electrons going here. And so we'll just label it. Here's the oxidizer, here's the reducer, here's the reducer, here's the oxidizer. The reducer and the oxidizers, there could be combination, and this combination is important. Nitrate with the H+, right? NO with the water. The combination is important because it's like if you try to make a cake. I've used this analogy many times, but if you try to make a cake, but you ran out of sugar, so I'm just going to make the cake flour. Are you really going to make a cake? No. Or make that. Let's say I ran out of milk and eggs, right? Is it going to work? No. And so it's the same thing. If you don't have this H+, it's not. Is it going to work? No, you're missing a key ingredient. If you're missing a key ingredient, it's not necessarily going to work. And then we compare. We just use the chart to compare. Which one's stronger? Well, it turns out that this is stronger. than this. So we're going from stronger to weaker, and then this has to follow stronger to weaker, and it does. And so this is the driving force. A lot of people will say, hey, isn't the driving force gas formation? Is the driving force gas formation? No. No, not in redox. Redox, we can't use gas formation as a driving force. Right? It's a different driving force. This is why I separate the reactions the way I separate them to keep the driving force the same for that basic type of reaction. It's like this. If I take two H2O liquids and form two hydrogen gases plus an oxygen gas, I'm generating 3 moles of gas for every 2 moles of water. That should be a huge driving force, right? But is it? Is 2 moles of water, 36 grams, going to decompose into how many liters of gas? About 75 liters of gas. So you take 36 milliliters of water, and that's going to spontaneously produce 75 liters of gas. Is that going to happen? Well, we're going to produce a lot of gas. 75 liters of gas is a lot of gas, isn't it? From just 36 milliliters of water. No, is that right? Yeah, 36 milliliters of water. So redox, we don't care about precipitation. We don't care about gas formation. We don't care about going from stronger acid to weaker acid. We only care about one thing, that is stronger oxidizer to weaker oxidizer. What time is it? Let's take another break, sorry. Let's take just a 10-minute break now. Or